Namaste. Welcome to this channel Chemistry Made Easy by Dr.ARM. We were discussing this theories of acids and bases. Under this title, we are going to see hard and soft acids and bases. So up till now we have seen various original or old theories of acids and bases, such as the Arrhenius theory, the Lorentz concept, Levy's concept, and other concepts such as solvent system, etc. And now we are going to see relatively more advanced concept of acids and bases. In order to understand what is this hard and soft concept of acids and bases, so we will see one example, and we will begin with this example here. So in order to understand this concept, we should know that, or we should understand that the acids and bases are having their intrinsic strength in order to exhibit their acidic and basic characters. But in addition to this, the acids and bases behave or observe some different properties which are also showing or determining the extent of reaction. So when we consider variety of reactions between acids and bases, the behavior is not same. The properties exhibit that the extent of reaction can be of different nature, and this can be studied on the basis of this concept. So we will see the example of halides. That is, if we say this AgF solid, so after dissolution in water, when we are dissolve this in water, we observe that it gets solvated Ag plus, it gets solvated as Ag plus, that is aqueous, plus this F minus aqueous. So this shows, means after dissolution, it shows the KSP value, that is solubility product value, it is 205. So we know that KSP value is the product of ionic concentrations raised to suitable power. So this will help us to understand what is the extent of solubility of a salt, whether it is completely soluble, partially soluble, or insoluble in a given solvent. So this can be understood with the help of this concept, that is KSP value. Again, second is AgCl. So this is also solvated in the same way, giving us Ag plus aqueous plus Cl minus aqueous. And here the KSP value is 1.8 into 10 raised to minus 10. 1.8 into 10 raised to minus 10. Then the third is AgBr. This, after dissolving in water, also give us the Ag plus as aquated ion, and Br minus also as aquated ion, and it's a KSP. The KSP value is again lower than this, and it is 5.2 into 10 raised to minus 5.2 into 10 raised to minus 13, 10 raised to minus 30. And the next reaction is AgI. solid, which also on dissolving in water gives us the product Ag plus aqueous plus I minus aqueous, and the Ksp value is 8.3. Ksp value is 8.3 into 10 raised to minus 17. So, if you observe these reactions and their solubility products, so if we compare this reaction with this reaction with this, and if we compare all these reactions with each other, they show that their Ksp values are different. In this first case of AgF, the Ksp value is maximum, that is 205. In case of AgCl, the Ksp value is lower, it becomes 1.80 to 10 raised to minus 10. In case of HBr, the Ksp value again decreases. It is 5.2 to 10 raised to minus 30. In case of HEI, the value is again lower. It becomes 8.3 into 10 raised to minus 17. So in this way, the Ksp values are found to be different. So this indicates that the AgF when dissolved in water gets more ionized, means more solvated. So the degree of solvation of Ag plus and F minus is maximum compared to other salts. In this case, AgCl is more solvated than remaining to AgBr and AgI. Similarly, AgBr is more solvated than AgI, and AgI is least solvated in water. So this gives us the degree of solvation. So this degree of solvation also depends upon the interactions taking place between the halides and silver ions. So here the interaction is taking place more between this Ag plus and F minus with the solvent molecules. So it gets easily solvated. But the affinity we can see for bonding or binding the two ions Ag plus and F minus is least here. Is least compared to other ions or salts. In this case, we can compare that the AgI is more strongly bound. Means Ag plus and I minus are strongly held together, so that after dissolving in water, they are not easily solvated. So this indicates the strength of bond between Ag plus and I minus. So in this case, the strength of bonding between Ag plus and I minus is powerful than in this AgBr, than in this AgCl, than in this AgF. And in case of AgF, the strength of bond is much more weaker, and therefore AgF is relatively much better or strongly ionized or strongly solvated. So this interaction can be, in this interaction between the cations and anions is much easily explained, very easily we can say, using the concept of hard and soft acids and bases. In order to understand what is this hardness or softness, so if we see, we are using here the hard and soft concept. So here you can consider the simple concept or ordinary concept of hardness. So if you consider this wall, this is much more hard because the surface of this wall is not easily deformed. Means we cannot remove any part of that surface very easily, or we cannot change the location of that part very easily. Similarly, this surface of the board is also hard. It is not easily deformed. But if we see the duster, this duster, we can press it very easily. Means we can deform it very easily. This is because it is called soft, and this surface is called hard. So similarly, this hardness and softness is of general sense. But if we consider the hardness and softness in case of atoms or ions of different elements, then it shows that there are the cations or anions which are having the inert gas configuration, we can say, which are having inert gas configuration. For example, here F minus, has attained the neon configuration, which is highly stable, and therefore the electron from this F minus cannot be easily removed. Means electron cloud of fluorine cannot be easily delocalized. It is strongly concentrated on fluorine, but it cannot be removed or withdrawn or delocalized from the electron cloud of fluorine, and therefore it is called hard. This is called hard. Similarly, we can consider another, that is H plus. So this H plus has no electron, and therefore its surface is also stable. It is not easily polarized. Means, instead of saying deformed, or we can say the surface is not polarizable. Means this H plus is electron cloud, we can say this electron cloud of H plus or F minus is highly stable. It cannot be deformed. Means the cloud, electron cloud, is not easily polarizable, and therefore such species are called hard. And these hard species are smaller in size. The size of such species is smaller, and they are non-polarizable. These are non-polarizable. Means we cannot add electron. We cannot add any more electron here, or we cannot remove any electron from this F minus. Similarly, H plus is also highly stable. It needs no electron, or it cannot have capability to donate electron anymore. So these are called hard species. In case of iodine, if we consider another species like I minus, or we can consider here cesium ion, or we can consider here the Ag plus ion. So if we see all these ions, then you will find that the valence chain of all these species, means the, first of all we will say that the size of these species is very large, and because of this they do not have the nearest inert gas configuration. Means all the valence chain are not completed. Means there is either vacancy of some electrons, or we can say some electrons are more than the inert gas configuration, and that is why these species can show deformation. Means the electron cloud of these species, maybe either I minus, cesium or Ag plus, may be polarizable. Means the electron cloud of I minus can be polarized. Means this can be attracted towards cation. So in this way we will see if the H plus is there. So if H plus is there and this I minus is there, then say this is the electron cloud of H plus. This is the electron cloud of I minus. So this is normal shape of H plus and I minus. But if we consider the polarization, so H plus is strongly polarizing. It has capacity to strongly polarize the I minus. Means the nucleus of H plus imparts the strong attractive force on the electron cloud of I minus. So that is why the electron cloud is moving towards this H plus. So this is called a polarization. So this is expected shape of electron cloud of I minus when it reacts with or interacts with H plus. The shape of H plus does not change, but nuclear force of attraction exerted on the electron cloud of I minus attracts the electron cloud. So that the electron cloud is attracted towards H plus. So the shared electron, the electron cloud, this electron pair we can see, is slightly shifted towards H plus, and that is why it acquires covalent characters. But in this case, the H plus and F minus both are hard species. So when they are interacting with each other, the electron cloud does not get polarized, and therefore the electrons remain as it is in F minus. So these are completely ionic species. These are called, and the nature of bond is called ionic bond. But in this case, the electron cloud is not stationary or stable on ions, but it is pushed towards H plus. So it is polarized, and because of this, it imparts the covalent characters. So the bond is not completely ionic, but imparts or acquires some covalent characters. And the magnitude of covalent characters acquired depends upon the size of I minus, charge on it, size of I minus or any ion, and charge on it. So larger the size of I minus, the covalent characters are more. Similarly, oxidation state of this anion is smaller, like F minus. It is harder species. But oxidation state when increases, the covalent characters also increase. Means the degree of polarization of the I minus electron cloud also increases. So in this way, the ionic bond does not remain 100% ionic in nature. It acquires some covalent characters, and that is why such observation is made that some salts are more soluble in water, whereas some salts are less soluble in water. So the species which are having this type of cloud, we can say here I minus anion is covalent, having covalent nature, means it can be easily polarized. So this can be also easily polarized. Ag plus is also easily polarized. So here ionic characters are more, and that is why it is very easily dissolved. But as we move from AgF to AgCl, the ionic characters are less compared to AgF. So its solubility decreases. Again, if we consider AgBr, the ionic characters are again decreasing, covalent characters are increasing, and therefore it is again more insoluble in water. AgI is again more insoluble in water, and this is because the nature of solvent also. We are using here water as a polar solvent, and if we consider another solvent, non-polar solvent, then the change is reverse. So this will be more soluble, this is relatively less soluble, this is less soluble, and this will be least soluble. So the behavior of salts depend upon the nature of solvent also. So here we might have understood this behavior of salts depends upon the size of the ions, then charge on the ions, as well as the characteristics, means properties of the ions, that is solvent also matters the degree of ionization or solvation. Now we will see another example in which we will find that how the salts are behaving. Here we have seen just now the interaction between cations and anions, and on that basis we can see when the cation, is hard, anion is hard, means both are hard species, then the interaction between the cation and anion, that is interaction between this cation and anion, is strong. Whereas if the cation is hard, or first of all we will take the same species, harder, then soft, then also the interaction is strong. When one of the species, say this is hard, this is soft, then the interaction is weak, or in other words we can say when this is soft and this is hard, the interaction is also weak. So here for hard and soft interaction we will consider the example of, say, HF as we have seen earlier. Then for this soft combination we will see the interaction between cesium iodide. We have taken another example. In this case, if we see the hard soft combination, if we take this H and soft, that is HBr we will consider, or HBr, HI, etc. Then soft hard combination, if we take the cesium fluoride or any other species like cesium chloride also. So we can have such number of examples. Now here the space hardness of the species depends upon the size. Hardness of the species also depends upon the size. Here, if we consider the size of the species, that is for cations, then it is small, and the size of the species here for soft is larger. Here also the same case in case of anions. If the anion is hard, it is smaller, and it is soft means larger in size. So we can compare the size. Now if we consider the charge, then if we see the charge, how does it map? So in case of, say, if we take Fe3 plus, it is hard. Then Fe2 plus, it is soft. So these changes in the size also makes the large difference. So here Fe2 plus So these are the examples which will help us to understand the behavior of these acids and bases. So all these acids may be hard or soft are Lewis acids. We have to keep in mind that all these acids may be hard or soft are Lewis acids, and all these bases which are hard or soft are Lewis bases. So we have taken the concept of Lewis acids and bases, but it is extended in terms of hardness and softness. So here, if we consider only the anions, then we can show F minus, the Cl minus, Br minus, I minus. So if we consider the anions, then the size, say this is hard and this is soft, and these are having intermediate, means this is relatively less hard. So the degree of hardness so we can say hardness decreases in this direction. Similarly, if we consider the size increases in this direction. So this is the hardest of all these halides, and this is less hard than F minus. Cl is less hard than Br minus. I minus is less hard than Br minus, and I minus is softest of all. So if we consider the interactions of all these with H plus, then the H plus and F minus are both harder species. So in case of HF, this is hard, this is also hard, means both are hard species, and therefore these are showing different behavior, means they are strongly having ionic characters. So the softness or hardness depends upon the charge. Charge is same here, size is different, and therefore the species are less or more hard. Now if we see the colors of their precipitates, so if we see the color of this AgF, AgCl, AgBr and AgI, then you will find that this is white, this is also white, this is pale yellow, and this is yellow. So in this way we can have the colors. So we can explain these colors on the basis of their hardness. So you will find that AgF has this hard Lewis acid, soft Lewis acid. This is soft Lewis acid, and this is hard Lewis base. Here it is soft Lewis acid and relatively hard, means this is also a relatively harder species, but here it is soft species. This is soft species. Now because of this, the harder combination, the strength of the bond Ag plus F minus, the interaction is relatively here weaker. The strength, the interaction between this is relatively weaker, and therefore we can find that this is, means these are not more stable species, but these two species which are having soft combination, and here also soft, but comparatively compared to this, AgI is having stronger interaction with between Ag plus and I minus than Ag plus and Br minus. So this is strong intense color, that is yellow color is intense, but here it is pale. In this case both are white species. This is because the absorption of light, here the absorption of light takes place in UV region of the spectrum, whereas in this case the absorption of light takes place in visible region of spectrum, and that is why these are white in color and these two are yellow color. This is pale yellow, this is intense yellow. The pale yellow color means the absorption of light takes place in the visible region, but it is towards right side in the spectrum, visible region of spectrum. Whereas this yellow color means AgI shows absorption in relatively more intense color, means more towards left side in the spectrum. So the absorption takes place in the visible region towards this right side, and